obviously NO2 will be having a greater minus I effect. So could you once explain the third note point again? Yes, ma. See, when it comes to alcohol, whenever there are any minus I groups in the sense electron withdrawing groups present in the chain, then they will help us in increasing the reactivity. So how come they will increase the reactivity means, take the first example itself. This nitro group will withdraw the electron cloud right towards itself, and you will be having hydrogen, beta hydrogen, and this electron cloud, whatever it is shifted towards nitrogen, will decrease the electron density on the carbon. So this will help us in withdrawing the electron cloud from this carbon hydrogen bond, facilitating the easy removal of beta hydrogen, thereby increasing the reactivity. So the point where the reactivity of alcohols is proportional to minus I groups. The reason for that will be the minus I groups increase acidic character of beta hydrogen, thereby easy removal of this beta hydrogen in the last step. So among the four groups we have, obviously nitrogen is the one with greater electron withdrawing capacity, right? So the answer will be option A. Option A will be the most reactive alcohol towards dehydration, because the electron withdrawing tendency for nitro group will be greater when compared to the rest other groups. Anyway, these two are carbonyls. If you want to write down the order, minus I tendency, NO2 greater than CN greater than carbonyl groups, C double bond O groups. So how exactly these minus I groups are affecting means, they increase the acidic character of the beta hydrogen, thereby facilitating its easy removal. If it is easy removal, obviously the OH part will be removed with the help of attack of the proton. Whatever the H plus, it has to be removed by incoming base. Added to that, the decrease in electron density will also help the base to remove it easily, and that is taken care of minus I groups like NO2, CN, CH4, like the electron withdrawing groups present in the carbon chain. And this is minus I effect, right? So the distance from where they are acting also has an effect on the reactivity. So let's see an example in that point also. In the same sort of concept, based on the distance from where this minus I group is acting. So take down another example. Arrange the following. Arrange the following in decreasing order. Arrange the following in decreasing order of reactivity. In the decreasing order of reactivity towards dehydration. Towards dehydration. Here, that same nitro group present and different carbon atoms we have to consider. Like the minus I effect is only applicable to certain carbon number only, right? It's not equal on all carbons throughout the carbon chain. So let's take one by one. 1, 2, 3, 4, 5. So you have OH, NO2, and in option B you have OH, NO2, and in option C you have at second position. So you have OH and NO2, and in option D same, you have OH and NO2. So the distance also matters when it comes to the action of minus I groups. So take that also into consideration. What happened? But as the carbocation is formed, then shouldn't we consider the stability of carbocation as well? Here, here we are not mentioning whether it is by E1 or E2, right? If it is happening by E2 mechanism, obviously we are just trying to concentrate on the removal of beta hydrogen. Probably the reactivity might be through beta E2 mechanism only. since they did not mention E1, I'm not looking in point of formation of carbocation. Okay, we are just comparing the reactivities only. Okay, even if it is carbocation at alpha position, our nitro group will be, or our minus I group will be dealt at what distance it is present for like with respect to beta carbon. So that's why I'm not considering the carbocation point of view. I'm just considering whether it will increase the reactivity of this beta hydrogen or not. Definitely, if this nitro group is on the side of carbocation, it will decrease the stability. No doubt in that. CBDA, yes, very good. The order is CBDA only. So when it comes here, when it comes to C, you have adjacent position. So as the electron cloud is more withdrawn towards it, so whatever the hydrogen present on this position will be easily removed. So the order will be C greater than, and the next adjacent is B only, because on the second adjacent carbon it is located. So C, B, and between A and D is one carbon nearer to the OH group than in A. So CBDA will be our answer. C greater than, B greater than, D greater than A in terms of the reactivity. So how are we comparing the reactivity? The minus I effect. The minus I effect is inversely proportional to the distance. Even if minus I effect favors the removal of beta carbon, if it is farther away, it won't have much effect on it. So that's how we are trying to compare the reactivities over here. Okay, so this is one way to look into the reactivities of alcohols. So the main thing is when to consider what. So until most of the cases, the question will be obvious only. Whereas if they mention specifically by E1 mechanism, by E2 mechanism, then use the same thing. If they are not mentioning what is the possible product by what is the possible product formed by so on so mechanism, assume it as E1 mechanism and write the products. And when you are writing E1 mechanism, always look for rearrangement so that a stable carbocation will be formed. That is first thing. And the second thing is, if there is an alcohol added to that, any electron withdrawing groups are present, they will increase the reactivity by making the beta hydrogen more acidic. More acidic in the sense they will decrease electron density on the beta carbon, thereby making the H plus removal a simple task. So that's how this minus I effect will increase the reactivity. And obviously the distance will matter when we are doing inductive effect, because it is only applicable or has its effect till 3 carbons, not more than that. So as the electron density is shifting, it is easy to remove the hydrogen. Yes, correct. As the electron density is shifting towards the nitro group, less electron density will be there on the carbon, between carbon, like the carbon hydrogen, whatever beta carbon we have, less carbon density will be there. Because of that, the shifting of electron cloud from hydrogen to carbon in this sigma bond will be easier, and H plus can be easily removed. Yes, shifting of electron cloud is the point when we are considering the minus I groups on alcohols. Yes. Okay, that is one point. And one more point is that whenever you have tertiary carbons, okay, one more note point, same thing, take it as fourth note point. So whenever you have tertiary alcohols, okay, they are very highly reactive. They are very highly reactive because they have a more stable carbocation. So they can undergo dehydration. They can undergo dehydration, means removal of water molecule, even in the absence of dehydrating agent. Even in the absence of dehydrating agent. Even at regular room temperatures also, the dehydration is possible when it comes to alcohols. So but we will be using a catalyst like copper, something like that we will be using. So if we take a simple example, tertiary alcohol, CH3OH, CH3 and CH3 on taking copper and heating, easy removal of OH will happen. Copper is not a dehydrating agent, right? So even in that scenario also, we will have an alcohol. This is only specific for tertiary alcohols. Why? Because they are highly reactive when compared to secondary and primary. Okay, keep that in mind. Even in the absence of dehydrating agents, even in the absence of dehydrating agents, the alcohol will be converted into alkene by the removal of water molecule. This is specific for tertiary only, so don't take this reaction for secondary or primary. Specific for tertiary only. All right. So this is one thing. Yeah, I'll wait a second. Please note this down, and then we will see this part. Uh, Next reaction method we will try to see. And most of the cases, when it comes to deciding even or E2, the question itself will be very obvious. Okay, they will give easy questions only. Just by looking, you can judge whether in this molecule we can do rearrangement or not. So if rearrangement is possible, we can move forward with the even reaction. If rearrangement is not possible, we can just move on with the E2 mechanism. So from the question itself, you can try to judge the type of product form. Oh, 9:20 already. Okay. Okay. So this is the second preparation method, right? Now let's see the next preparation methods of alkene. So first one was dehydration. Sorry, first one was dehydrohallucination, and now we will see, we have seen dehydration. Now let's start the third preparatory method of alkene, that is from quaternary ammonium compounds. Quaternary ammonium compounds. This is going to be a little bit different from rest of the preparatory methods of alkenes. Why? Because here the major product will be Hofmann product. Okay, that's why this reaction has another name, Hofmann elimination. Hofmann elimination reaction. So from quaternary compounds, we will get alkenes by Hofmann's elimination. What am I writing? Hofmann elimination. So let's see how the reaction will happen. Okay. So take down. On heating quaternary ammonium compounds, this is the next preparatory method for your understanding. On heating quaternary ammonium compounds, on heating quaternary ammonium compounds with a base, alkenes are formed. With a base, alkenes are formed. Okay, the statement is simple, like one line statement only, but while writing the products, we have to take care of this ammonium part. Why exactly ammonium, quaternary ammonium part means? I will show you an example. So what does quaternary ammonium means? It's just like quaternary carbon attached to three other alkyl groups. If it is attached, sorry, four other alkyl groups. If it is attached to alkyl groups, obviously it will be bulkier. If it is bulkier, what will happen? There will be a steric hindrance, which means during the course of the reaction, there is some this steric hindrance factor has to be considered while writing the major product. So let's take a very simple example. Okay. So, okay, I will directly write the reaction. So CH3, CH, CH, CH3, and here you have CH3 taken twice, and this is quaternary ammonium. This will have a nitrogen will have a positive charge, and the whole molecule is attached to the O minus. Right. So this is the group. Don't take the brackets, but for your understanding, I have written the brackets. So this is quaternary ammonium because the nitrogen here is attached to three alkyl groups on one side, three methyl groups, and the other isobutyl group. So in this particular compound, sorry, not isobutyl, just butyl group. Now, in this particular one, the nitrogen is attached to four other carbon atoms, making this a quaternary ammonium. Ammonium means positive charge on the nitrogen, and OH minus is the counter cationic part. Now, in the next step, what will happen is, obviously this will be our alpha carbon, yes or no, because the nitrogen group will be treated as substituent, and that is our alpha, our beta 2. So if the elimination of hydrogen happens from beta 1, the product that we expect is CH3 CH3 CH CH3 CH double bond CH CH3. Now, if the elimination happens from beta 2, we expect the product as CH3 CH2 CCH3 double bond CH2. Right? So, what is the most substituted alkene? This one is the most substituted alkene, right? This should be our product according to the Sage-Zef group. But in reality, for this quaternary ammonium compounds, this will be the major product, and this will be the minor product. Why? What's the reason? It's obvious from the type of substituent we have at the alpha position. This is, I'll write you CH3 CH H CH nitrogen. CH3 CH3 you have, CH3 you have, and then you have CH2 H. All right. So here you'll have a base, and we'll be hitting it. So this is beta 2 hydrogen, and this is beta 2 hydrogen, and this is the beta 1 hydrogen that we have considered. So there is steric hindrance offered by the substrate itself. So whatever the base we have, to that particular base, the internal beta hydrogen cannot be approached because of this bulkier group. So whatever the hydrogen, beta hydrogen available, the nearby one, the base will be attacking it, and that will be removed as base and H. So that's the reason why we end up having product number 2 as our major product. So 1 and 2. So this base will be approaching this one. You have CH3, CH2, CH double bond, CH2, wait, CH. So CH2. This quaternary ammonium will be withdrawn something like this. This electron pair will be withdrawn by the nitrogen with the positive charge. It will be removed as N CH3 taken thrice. You have a lone pair, and the base will be removed along with the H that was being removed from the carbon, beta carbon. So the steric hindrance from the ammonium part, the quaternary ammonium part, especially will block the approach of base towards the internal beta hydrogen, or where there is more branching possible. And because of that reason, the base will remove whatever the beta hydrogen is available to it, and ends up in the least substituted alkene as our major product. So we will have but1ene as our major product. This is the least substituted alkene, right? And the least substituted alkene is a Hofmann product, and that's the reason why this reaction is called as Hofmann elimination reaction. Please note there is no alkyl group here, like it's just but1ene and but2ene. Okay, did you understand what's happening over here? because of the bulkier nature of this quaternary ammonium, there won't be space for the base to approach the beta carbon, which might result in more substituted alkene. That's the reason why the nearby beta hydrogen will be removed, and because of that we end up having the least substituted alkene as our major product, which is Halfman product. Halfman in the sense the substituted one. So this is quaternary preparation of alkenes from quaternary ammonium. So ammonium part will be converted into like tertiary ammonium trialkyl amine with a lone pair on nitrogen, because N plus will be compromised, plus charge on nitrogen will be compromised by the withdrawal of the electron pair. And during the loss of this hydrogen, this electron pair will be coming over here, right? So that will compensate the electrons required for this pi bond formation. So likewise, try to write a product for this one. So you have CH3 and you have N with a positive charge on the same position. CH3 taken thrice. So where do we use that OH minus? Is that a base? Yes, it's the base. Instead of base, instead of if I use OH minus here I'll have OH2O as the product. So this base is OH minus. Acha, if you are talking about this OH minus, no, this is not the base. This is the part of quaternary ammonium hydroxide. Like ammonium has N some X or R group taken 4 times with plus, right? So the negative charge can be either H minus or OH X minus or OH minus, hydroxyl or halide it can be. So this is not the base, this is part of the compound, part of the neutral compound, not the base. Cationic part is our ammonium and the anionic part is the hydroxyl. Base is separate. If the base we are using is some KOH or NaOH, something like that, the beta hydrogen will be removed as H2O. The anionic part has nothing to do with the reaction. Even that will be removed. Let me write here. Even that will be removed. Let's say, yeah, as H2O, that will be removed because we didn't write the specific base, right? So this is not the base. The anionic part of the compound is not the base. Base we will be using externally. We will be adding the base and we will be heating the mixture. Yes. So for this component, what is the possible product based on Hofmann's elimination? On the same carbon, you have methyl group and ammonium group. So give it a try. There are 3 beta hydrogens possible of them. So we have a base OH minus, okay, and we are heating it. So what might be the possible product? Okay, along right. So we have quaternary ammonium nitrogen with a positive charge over here. So this is our beta, because this is our alpha carbon, right? So this can be our beta 1. This can also be our beta 1 because both of them are equivalent position, and this will be our beta 2 carbon. So if the elimination happens, hydrogen elimination happens from beta 1, we have a product which looks something like this. Yes or no? And if the elimination happens from beta 2, so beta 2 hydrogen removal, the product will look something like this. Beta 2 is this one. So double bond, methylidine cyclohexane. And because this quaternary ammonium part is a bulkier one, the major product will be the least substituted alkene, which is product number 2. So this will be the major product. And this will be our minor product, because the base cannot approach either this beta carbon or this beta carbon because of the bulkier texture of our ammonium part. So it will remove whatever carbon is available easily, the nearby one, and that will lead to least substituted alkene as our major product. That's why the preparation of alkene from quaternary ammonium compounds, it's given the name. It is by Huffman's elimination, indicating the major product is the least substituted alkene. So clear with this method, right? Anyone having any doubts in this part? Okay, so if it is clear, we can move on to the next preparatory method. Okay, it's 33. Okay, we'll write the statement. We will see one example and explanation part. We will take it tomorrow. Okay, so take down the next preparatory method, that is 4. So can we say that the first compound formed is more stable because it's endocyclic? Hmm, the thing is, it can be stable obviously because it is more substituted, but because of the type of reaction we are uh, seeing here, the major product will be Huffman product only. Obviously this is the more substituted alkene, obviously it will be stable, but its formation is not favored because of the type of reactant we are using. Yes, this is endocyclic, and the other one, the major product is through exocyclic elimination only, but not the major product. The stable one is not the major product because of the bulkier part of the substrate, leading to least substituted alkene as our major product. All right. Next preparatory method, please take down dehallucination part. This is also elimination, but both the groups, both the living groups will be halogens only. So dehallucination of vicinal dihalides. This vicinal dihalides part we have seen. So what do we mean by vicinal? Dihalides means it's obvious two halogens are there. So what do we mean by vicinal? Ammonium, the major product will be endocyclic only. Ma'am, usually if there is no bulkier ammonium, the major product will be endocyclic only. Yes, definitely. That's what we have seen in the hydrohallucination part, right? If there is no hindrance, always the major product will be endocyclic only for cyclic compounds. Yes, your statement is correct. Yes. So what do we mean by vicinal dihalides? Vicinal means nearby or adjacent. So dihalides means two halogens are present on adjacent carbon atoms. And dehallucination means the removal of hallucination part. So everything we need to know regarding this reaction is in the statement itself. We are removing halogens from two adjacent carbons to end up with an alkene. So this can be any part of the alkyl chain, and you have two halogens on the vicinal position, in the sense adjacent positions. And now we will be heating this in presence of an alcohol, so that, and that too zinc will be zinc will be added. So using zinc, when we heat it in presence of an alcohol, adjacent positions which are substituted with halogen part, they will be removed as ZnX2. Since the halogens are removed, a new pi bond, carbon-carbon double bond will be formed, and that will be our alkene. So take down the statement. When vicinal, when vicinal dihalides are heated with, when vicinal dihalides are heated with zinc copper couple, zinc Cu couple, means both of them together we will be using in methanol. Methanol is nothing but alcohol, CH3OH. In methanol, pure alkene is formed. Just the removal of halogenation will be there. Pure alkene will be formed. So in the above example, it's just a model example where we are trying to write the vicinal part, that is halogens on the adjacent carbons, and they are removed by the zinc as ZnX2, and the valencies are satisfied by a new pi bond formation. So if you want to take a proper example, we can take 1, 2 dibromoethane. This is Br and this is Br. So 1, 2 dibromoethane or ethylene bromide also we can write. So here we are heating. Zinc is directly involved in the reaction. So methanol is CH3OH. On heating, these halogens, both the halogens will be removed with the zinc as ZnBr2, and the leftover valencies will be satisfied by CH2 double bond CH2. We end up having ethene, and ZnBr2 is the elimination part. I mean, how Zn removes the bromide part of the vicinal dihalix. So from the adjacent carbons, we are trying to remove the halogens. Okay, so this is one thing. Okay, take down one more example, and with that we will wind up today's class. Tomorrow we will see some more information regarding dehalogenation of vicinal dihalides. Okay, so CH3, CH2, CH2, Br and Br. So it is obvious here. CH3OH, on heating you have CH3, CH double bond CH2 plus ZnBr2. Excuse me. So what is the role of alcohol? What's the role of alcohol? Mm, it's a solvent. Okay, probably it will facilitate the removal, the reduction part of the zinc. Sorry, the oxidation part of the zinc. Probably. Mm, how can we justify the alcohol's presence? Br minus, Br minus, OH. Uh, Probably it will helps for the zinc, like zinc is a metal, right? Probably it will helps for the reaction to move forward. Zinc as a whole in a solid form we cannot use it, right? So we will be using a methanol solution of zinc and copper together, so that the reaction, the zinc can easily involve in the reaction. Probably that's the reason. If we use another polar non-polar solvent, then the zinc cannot interact with the reactant. So probably for the ionization of zinc to Zn plus 2, the methanol will help. The polar reactant, so the polar solvent will help in the ionization part. Once the ionization is done, then we can have an alkene after that. So how much more is left in the alkenes? We do need to discuss some 3 to 4 more preparations of alkenes. So I'm thinking about 1 or 1.5 hour, not more than that. And after that, we can see about chemical properties. So around 7 to 8 more classes altogether is required for alkenes. So shouldn't we use zinc and copper together? Yes, zinc and copper together will be used, but zinc is the one which is undergoing the changes from Zn0 to Zn plus 2, the oxidation part where it gets added to Br bromide groups. I think copper will be just as like it won't involve in the reaction, but it will both of them together will be used. But the one converting from plus 2 to plus 0 to plus 2 state will be zinc, because the bromides have to be removed, right? And that is taken care of zinc only. Yes, copper and zinc together will be used in the reaction, no doubt in that. Okay. So yes, that will be for today. Tomorrow we will see some more like another halogens can be used. Not geminal halides can also be used for the same dehalogenation part. We will see those reactions. Added to that, another solvent mixture can also be used. And we will see whether this reaction is stereoselective or not. So all this stuff we will try to do tomorrow. And after that, we will see another preparatory methods. Preparatory methods will take hardly 1 more hour, not more than that. And after that we will go for chemical properties. Chemical properties are important. I told you right at the starting of chapter itself, the stereoselect, the mechanism part of the chemical properties are important in alkenes chapter. So that part we will try to concentrate. Okay, so that will be for today. We will meet again in tomorrow's morning session. All right. Yes, one more thing. Exam is on Sunday, not tomorrow. You hope you know you got the information. Exam is on Sunday. Tomorrow we have as usual classes. So we will try to finish the syllabus, revision and all. You guys have to take care. But I'll be available to clarify your doubts. All right. Take care, ma. We'll meet tomorrow morning. Yes, we do have parent meeting in the afternoon session. So come according to your slots, okay? Because other faculty will also have batches, other batches, not only J7. So if you come along with the slots, it will be helpful for them to arrange and all. All right.
Thank you, ma'am.